Hi there, I thought you could use a little refresher. This is section 15.5. This particular problem, I didn't write it out properly, but we'll make do. This is number 27 on page 971, which is section 15.5 in your text. It asks you to compute the directional derivative of the function at the given point in the direction of the given vector. It also tells you to be sure to use a unit vector for the direction vector. I also asked you for the gradient because that's in the section as well. So what the gradient is it's a vector, and it's the partial derivative of x and the partial derivative with y. And sometimes I just say find the gradient, but sometimes I'm going to say find the gradient at a point. So we'll go ahead and do at the point this time. So let's say find the gradient at the point 1, 2. Okay, so that's where we're going to start. So it's actually really easy. So we're going to say the partial derivative with respect to x of this function would be 6x. And the partial derivative with respect to y of this function would be 2. Okay, my point is 1, 2. So this value right here, when x is 1, and I'm getting that because that was the point that's given, this would just be 6. And of course, 2 here would just be 2. But remember, the gradient is a vector, so you have to write it in vector form. So this vector is 6, 2. This gradient is 6, 2. So just refreshing your memory, that's how you find the gradient. Now the reason I asked you to do the gradient is that the gradient is a component in the directional derivative. So you can see that I kind of gave you the little formula behind it. This is, see if we can fix that. Phew. This is your gradient. So now that I have the gradient, the first part of the directional derivative is done. That's going to be, let's go ahead and write it first. Six, 2. Oops, fix that again. Okay, now this is a dot product. So a dot product is a scalar quantity, and that's going to be really important. It's a scalar quantity. So the gradient is a vector, but the directional derivative is a scalar, because remember, it's a slope. Okay, so it says in the direction of negative 3, 4. You cannot put negative 3, 4 here. The reason you can't put negative 3, 4 here is it's not a unit vector. So you have to make it a unit vector first. So let's call it u for unit vector. The unit vector, to find it, let's do this first. So we're going to have negative 3, 4. We're going to put it over to make it a unit vector. I'll get it right in a second, sorry. Cal 4 online, it's not my cup of tea. There we go. So to find the unit vector, I'm going to take negative 3, 4 and put it over its magnitude, which of course would be the square root of 9 plus 16, which would be 25, square root, which would be 5. And so it would be negative 3/5, 4/5. So finding this directional derivative, we would multiply it out and get negative 18/5 plus 8/5, which would be negative 10/5, which is negative 2. And so your directional derivative is negative 2. And of course what I have right here is just a dot product. So I multiply 6 times this, and I get negative 18/5. And then I'd go back and I'd multiply 2 times 4/5. That's how I got the 8/5. This is your directional derivative. Okay, and that was, I think, section 15.5. So you also had increments and differentials in the next section, and we worked those before spring break. and we did a terribly ugly proof value of it, and I said I don't know how I'll test it, so I made up my mind. And so it'll be tested something like this. So for the first part, I asked you to find the approximate change. I gave you a function, z here, and I told you that the point xy changes from 1,4 to 1.1, 3.9. Now your approximate change, dz, is actually this formula right here. So let's do that part first. So the approximate change, dz, is going to be the partial derivative with respect to x. So that's going to be 2 minus 2y. We're going to multiply that times dx. And then it's the partial derivative with respect to y, which would be negative 3 minus 2x. And we'll multiply that times dy. So that's how it would look. So I know up there that x is 1 and y is 4. Okay, that's how I got that. I know that dx is 0.1, and I know that dy is negative 0.1. So we can plug those values into our dz formula. 2 minus 2 times 4, which would be 2 minus 8, which would be negative 6, times 0.1. Okay, so there's the first one. And over here, we're going to have negative 3 minus 2, so that's a negative 5, times a negative 0.1. So two negatives make a positive, and that's going to be a positive 0.5. When you put these two together, you get a negative 0.1. That is your approximate change, which we call dz. So let me change that for a second. dz is actually negative 0.1, but this is approximately the change in z. Now, so that part I will ask you on a test. It's not hard to do, just simple calculations. And that was your answer to this one. So the second part asks you to find the exact change in z using your calculator. So I'm not going to ask you the formula way. We have enough going on to have to deal with that. So if you plugged in the point, let's do it this way, z at the point 1, 4 would be, it looks to me like it is negative 18. So if you looked at it, you'd get 2 times 1 minus 3 times 4 minus 2 times 1 times 4. So you get 2 minus 12 minus 8, negative 18. Okay, so that's that one. But you also need to find z at the other point, which is 1.1, 3.9. So if you plug that in, you get 2 times 1.1 minus 3 times 3.9 minus 2 times 1.1 times 3.9. And what you should get is negative 18.08. Okay, so then you have to find the change. Okay, and so the change in these, let's see which way we subtract them. We're going to get a negative 0.08. That is the actual change in z. So you want to do your second function, or z of 1.1, 3.9 first, minus z of 1, 0.4. And that gives you a negative 0.08, which is very close to our estimate of negative 0.1. And that's how it will be asked on a test. That's how it looks.